So finally we get to do some CSV at the end of the conference. So who was here the talk before me about all the good things in annotations? So, yeah. So I do recognize that, and it was actually a nice segue into somewhat of a crusade that I found myself in. Well, first starting on one small thing related to obviously marshalling and XML and other things, and sort of coming on more and more things that always felt quite out of place in how you deal with these things in the mainstream frameworks in Java. So we'll kind of see where that journey got us. So first I want to talk a little bit about, hopefully, what many of you will recognize in how you would deal with XML if you were writing a Java program. And then sidestep a little bit into a framework called Akka and its streaming part, which actually forms a cornerstone of the approach that we're taking. Then building on that to see how we can represent our XML and other stuff and the objects that result from that as streams rather than as single entities, which is really what this is about. And look at how that's applied in one of the more complicated use cases that we originally had. Just to get a bit of an idea, who here has never heard about Akka before? Okay, great. So we'll get into that. We'll give me a bit of a way to time things. Just a little bit about Tradeshift, the company I work for. We are a global platform for business interactions. Originally started out from electronic invoicing, but sort of grew into both sides of the business interactions happened before and after, and now we're helping more and more companies globally to exchange documents online and work together to achieve more commerce. One of the big parts that Tradeshift is built on is an XML standard called UBL, the Universal Business Language, which is published by Oasis, and is a horrendously big combination of what invoices all over the world could look like, and orders and other things. But that forms sort of the basis of the more legal interactions, and also the use case that we're going to touch on today. Since you might think of an invoice as a fairly simple thing, like a 1 or 2 page document that says, well, you bought this and this and this, please pay for it. And that's generally true, but as things get more electronic, it's actually convenient to bundle that invoice up together with other things. There are these individual contractors that use their invoices also as a proof of documentation for the work that they've done. So you have like this kitchen builder or somebody who repairs your electricity and taking a picture of the stuff that he changed and put those JPEGs together with the invoice into one XML file as attachments. And that's what in the end gets processed on Tradeshift. And we have to process that thing as one unit of work. And as you know, electronic invoicing and electronic documents keeps increasing, the size of these files that we're seeing also increases. Now, historically, the way that our system was written, we use a plain old Java Spring-based backend when we started, and we use the XSD that comes with UBL, which describes the invoice in all these weird and wonderful ways, generate Java classes from that, and use that to read in our invoice document. But if the invoice is 100 megabytes big, then the resulting object tree is at least that size, usually factor 2 or 4 more. And as you may see that, you know, in your average modern Java program, you can read a few of those documents in simultaneously, but as things grow, this starts to break down pretty quickly. That's also what we're seeing, memory usage increasing, and a big part of the system actually isn't interested in those attachments at all. It's interested in the semantic content of the invoice. And yeah, sure, there might be hundreds of megabytes of images of cats also somewhere related to this invoice, but we actually don't want to deal with those in most cases. But let's step back a bit and look at how JXB actually works internally. Who of you have not used JXB before to do XML with Java? Great. Some, but then I'll quickly go through this. So say that we have a person class and we want to represent that as XML. What you do, and you've seen this before, is you slap on a few annotations here and there. And one thing I should mention is that, you know, we're writing modern Java, so our person is actually immutable. There are no setters. If we wanted to do something else, we create a new person and change the fields in there. And so we do this, and we think, okay, this is great. Now we can read and write persons. We need the empty constructor to make JXB happy, and things work. Except they don't, because if JXB creates your object, so if it reads in XML and instantiates a person, it decides to drop a list directly into the address field up there. And that list will always be an array list. And remember that before we wanted to be immutable, so we wrap the array list in an unmodifiable list in our constructor properly, and then we can just, in the getter, return the unmodifiable list and regard it against modifications. It's no longer the case, because now when JXB comes back with the object, you always get the array list. Well, you inevitably discover that and say, okay, sure, then I'll just wrap it in my getter and things are rosy again. No problem. But then, our person object is not just a stupid DTO, and you figure, well, in different parts of our application, we actually need to display the first name and the last name of the person together. So we add a new method, get name, which returns that together. That's great, until we suddenly notice that the XML that we send out now suddenly has a name tag as well. Because the default behavior of JXB, if you don't do anything else, is it will inspect your object for all the public Java Bean properties, and get name as a Java Bean property. So it'll happily render a new name tag. So by just creating a method, you suddenly have changed your XML representation. And sure, you can change that by putting an XML access type none, which hopefully some of you have also seen before. But there are a lot of things that you just don't discover with JXB. You have to Google your way out of it, or Stack Overflow your way out of it, and find out how to do it. Another example. So we want to add the birthday to our person's XML representation. And we use local date for that. That's the Java type to encompass dates. But I'd actually like that to be represented not just as a string, as a one fixed attribute, but as a nice semantic thing, where say year, month, and day. Does anyone here know how to do that? I don't blame you. There's a thing you can do. I looked it up. There's an XML Java type adapter, which you can create as yet another annotation you can put on there, which has to implement an interface from the type you want to serialize to something else. It's actually going to be a DOM element, but we can't declare it to be a DOM element, because then JXB will complain that it has to be an interface. So you actually have to say object there, so you don't tell it what it will be, we just shove in a DOM document node in there, and then it will work. Not obvious. And the final problem is that we've released our application, we've bound this to our REST API. Now, things actually work, people are happy, people are using our application, and realize, okay, we actually need to change our API a little bit. And it's somewhat incompatible, so I want to introduce a new person namespace in XML, so that we don't have two versions of the API, and not to overdo things, I just want that to be under the same person's resource that I had before in the REST layer. And I just want to accept either. Right, it's completely valid. It's some HTTP level, you put XML in there, and if it's in one namespace, we do one thing. If it's in the other namespace, we're going to do something else. I couldn't find actually how to do this in JXRS at all. Well, besides getting everything in as a byte array and then just hacking your way around that with an if statement. So there are quite a few problems with the annotation-based way of doing XML. Which, by the way, occur in the same way for JSON as well, if you've used JSON or some of the other JSON-based frameworks. So, leaving this behind for a moment, I thought to myself, well, what if we could change this around a little bit? Like related to what was presented in the previous presentation, but from a slightly different angle. What if we could just write in, as fluently as possible in Java, to say, well, I have a person object here, and I just want to put the first name into this tag, last name into the other tag, and the address, which is a list, into a tag each of them out. And I started out by just trying to define a bit of DSL to say, okay, what would this look like? What kind of expressions could you write that would encompass just the marshalling behavior of a class into something that you could park anywhere, that would describe how to get that thing in and out of XML without relying on any magic like reflection or AOP or other shenanigans. And it turns out that what you have to write isn't that much. So imagine that we have an interface called write protocol, which is generic in two types. The kind of thing we marshal to and from, could be XML or JSON or CSV, and the object that will result from that, or the object that we're writing out, which in this case is person. If we're dealing with XML, you could then say, well, let's say that the protocol to write such a person or to represent such a person in XML. In this case, it's a write protocol, so we can only write this person to XML, so create XML from a person object. Well, we start with a tag in a particular namespace called person, and then the person's first name goes into an attribute called first name, person's last name goes into an attribute called last name, and I want to iterate through the address of the person, and for every element in that iteration, I want to do another tag called address, where the body becomes what I found. I sort of describe what's going on here, and you may be able to read it, but the nice property of this is that this is actually a compilable Java expression, where every element of the I was hoping to move my mouse into, there we go. Where every row here, every expression here has a type. And most of these methods called tag and attribute actually themselves return a write protocol again. So attribute returns a write protocol from XML event and string, because attributes in XML are strings. And person get first name happens to return a string. So those types match. That's why it compiles for Java. But getAddress doesn't return a string, it returns an iterable string, or listal string, which is a subclass of iterable. So here we have another method called iterable, which will take a write protocol of a particular type and return a write protocol of an iterable of that type, just by repeating over it. So that way you can get collections of data, and it works in the same way for sets and maps with slightly different syntax. Yet, have the compiler check that everything that you're writing makes sense from a type system's perspective. And it has two great advantages. The first is that, as we've seen in the previous presentation, you can click all these things. If you think, oh my god, what does this do? You just click it and see, oh, okay, so there's a type signature, it takes this in, it takes the other thing out. So you can follow what's going on, and not be distracted by all the annotations where you can read the documentation, but we all know frameworks don't have any bugs and they always do what the documentation says. But the second advantage is that because these are expressions, if you think this is too complicated to write in one shot, you can just take any part of this, let's say take the iterable thing out, introduce a variable for that, and then use that later. We'll see some more examples going forward. But for example, there's an integration of this library that I'll be introducing, which is in a framework called TS Reactive. We're also moving into making it part of ECHA, so you can use it directly when you use that framework. But you can also directly use it with the standard Java XML libraries like stacks, where there's a wraparound stack, so you can just say, okay, I have a protocol here and a person, please make some XML for me, and that's great for unit testing. Now, the previous example, we could only write out a XML from a person, but what if we want to do both? Like with JXB, you can obviously read and write always. Well, we can more or less, we've told what we need to do, but there's one thing missing, which is to instruct our framework, okay, how do I actually instantiate a person object without going down to reflection? Well, there's a way to express that in Java. It's a lambda expression like everything else. So by using a slightly different variant of tag and changing the order of things around a little bit to make the type system happy, we can now have an additional argument here that is the lambda that tells us, well, once we've read an attribute, and an array list of some other things, then with these three things, how do I create a person with that? Well, we just called a constructor in this case. Of course, you may know that this expression you can also summarize by just saying person new, but I chose to write it like this to be a bit more explicit in this example. And again, now we can also read in some XML, which looks slightly different because the way these frameworks are, the way these protocols are set up is that it's actually possible to emit multiple times for something, which won't happen for XML if you have a root tag, but if you're matching some subtags, you can actually get all of them out as a Java stream. And you can, obviously, because you're completely controlling the marshalling, you can add the birthday example as well, which I'll skip over for the moment. Since I want to get into another part of the puzzle, which has to do with the memory usage and the scalability of dealing with bigger parts of XML. But now we've just done some fun syntax things. And for the scalability part, I'll talk a little bit about Akka streams. Now, I assume here that, well, let's just ask, who has never read from a Java I/O input stream before? Great. So there we know. So okay, if a stream, just think of an input stream. You can ask it, hey, give me some data, and that will block your thread, so it will sit there until some data is available, and you'll either get the data, or you get a 0, or end of file, or -1 actually, and then you're supposed to stop. Which is great. It's easy to code against, but it's a problem, as you also may have read on your favorite blog, since if you block a thread just for doing I/O, that's a little wasteful, because it means that you can have about 100 or 1,000 such I/O things per server, and then your server's memory is filled up by doing nothing except the stacks that have to be allocated for all of these threads. So what if we could do some streaming stuff without having to block a thread? Now, ideally, I'd want to do my streaming stuff without having to tell my framework to get something or wait for something at all. And that's what Akka streams try to give you, like a way to express what you would do with each element in the stream without you having to explicitly say read from here or write to here, or in fact do any kind of flow control yourself. With Akka streams, you generally don't have to say, okay, I want to get some more elements because I need them here. You write your streams in separate units that you combine to achieve a certain effect. And for that, let me introduce a few terms. So in Akka streams, the place where a stream starts is always a source. And the source is not like input stream, a source of bytes or byte buffers. It can be anything, any kind of T. Source is generic in T, and T may be bunches of arrays of bytes if you're reading something from a file, but it could also be your own object. The second thing that you will encounter is a flow, where a flow has both an input and an output, which can be of different types. The input can be T, the output U, and it's up to the flow what to do with that input and the output. So it doesn't mean that if you send something into the input that you always get something onto the output immediately. Maybe every second item you put into the input appears on the output. Or maybe if you put something on the input, it appears on the output 1 second later, since actual time and the environment can be a factor in how these things operate. And that complete freedom is very special in setting up the stream, because anything potentially can affect what it actually does. It can use system loads to make decisions. It can change its parallelism depending on what's needed. And you may not always need that, but it's good to have these in your toolbox. But in order for the stream to actually finish, something has to, in the end, consume all the data, which is a sink. And a sink is an element that only has one input. And you obviously put these things together to make a complete processing framework. And when everything is wrapped up together, you can say to Akka, okay, go, please run this. And then really Akka will look at these sources and flows and sinks in the processing graph and figure out, okay, how many buffers do I need in between these things, and how much can you read here, how much is waiting here, how much can we send on the way, oh, this one is doing a little slowly, maybe I'll stop reading from this source, or the sync is backed up and I need to delay here a little bit. All that flow management is taken care of by the framework, so you really end up only writing fairly small pieces of logic. I'll skip over the meta relation, it's not that important at the moment. But let's look at a simple example where we're just printing numbers that increase every second, and we want to see one number every second. And we start by actually, let's go through this a little bit differently. Let's start with the source. So there's a factory method built into Akka called source.range, which gives you a source of integers in between a certain range. So it will start with 0 and go to 1, etc., to whatever end you put in there. And as you may guess, this does not internally build an array list of a billion, gazillion integers. It will just emit them as needed. And source is a method called .via, where you can put in a flow, like a building block that comes afterwards, and it will return a new source, which represents the original source and the flow applied. In this case, we add a thing called delay, which we created up here, where we, the way to create flows directly is a little bit awkward. You always start with an empty flow that does nothing. In this case, a flow of integers, where if you put an integer in, an integer comes out. This is the flow that create does. And .throttle is the actual delay thing. So throttle is a built-in ECA flow that will throttle a particular stream by saying, okay, I only want so many elements per time unit to pass. And in this case, just 1 element per second will do it, but you can make this more complicated if you wanted to. So we say source.range, and that gives us a source of integers. Again, let's ignore the second type argument. .via delay, well, delay is a flow with integers in, and still integers come out. It actually doesn't do anything to the elements themselves. It just delays them. So we still have a source of integer after this. Then .to is a method that takes a sink, and that completes the graph, because if you put a source into a sink, you have something that is close and that you can actually execute. Our sink is called print, and that sink is defined over here, where we have another factory method in ECA called sink.forEach. That gives you a sink that runs a particular lambda every time an element arrives. In this particular case, we just print it. So whenever that sink will also work as fast as it can, whenever you send something into there, it will get printed. So after we say .to print, we now have a runnable graph, which is ECA's basic type for something that has no inputs and no outputs. So the graph is complete, we can run it. That's why runnable graph also has a run method, and that actually starts processing. Which, by the way, also means that as we're constructing this, so there are methods being called here, right? Source.range, .via this, whatever. That's only building a blueprint. It's building a recipe, what we want to do once we actually kick off the graph. It doesn't actually start any processing or opens any files or any kind of I/O that you've defined here. It's not until it's say run that the whole thing gets launched and starts executing. Are there any questions about this so far? Okay. Let's extend it a little bit. No, actually, let's skip over that. So we know a little bit what streams are right now, but then let's introduce our XML and JSON stuff again. So how would you represent an XML document or a JSON document or a CSV document as a stream? Well, a file as a stream is easy, it's bytes, so we just get bytes in. But a XML document, people have represented that as something more high level in the past. In event-based APIs or callback APIs, like the original document handler, it was part of SEX for quite a long time, where you just get callbacks whenever a parsing event happens, like a tag started, an attribute was found, some body content of the tag was found, an XML processing instruction. All those things were raised to the top level rather than the individual bytes that were in the stream. But it wasn't until stacks that there were actual Java classes that represented these events as actual concepts. So for XML, we actually have something we could put in a stream, which is the XML event class in Java. It does precisely what we want. It represents an immutable piece of one part that happened during the parsing of an XML document. So if you look at an XML document, you can represent that as a series of XML events. So those we could put into a graph, into an ECA stream. Unfortunately, I didn't find at least not a fairly broadly established equivalent for JSON and CSV. So we wrote something ourselves that does a similar thing for JSON, where you say, okay, JSON object started, JSON field started, array started, string value, a numeric value, and that's about all that JSON is. And again, the domain of JSON and the domain of XML aren't that big that it's very complicated to set these things up. But now that we have these types, we can think about, okay, what do we need in order to get from bytes, which we will get in on, I don't know, an HTTP request or in a file or our standard input or wherever we are processing from, and also what we need to send out again. How do we convert to and from these bytes to these XML and JSON events? Now, the writing part, which you see here on the right, so the flow from a particular event type to a byte string, which, by the way, is ECA's representation of a byte array that is not modifiable. Those things are not that hard to code up and write and wrap existing frameworks, because on the output side, these frameworks generally behave when it comes to threads. You have like your XML writer or JSON writer or whatever, and if you tell it, you know, please do start an object, write a field, write some value, close the field, it will typically send write commands to the output stream that you hook it up to. So you can in that way wrap it to emit bytes as a result of JSON events coming in. There's no thread blocking problem there, because as long as you provide an output stream that doesn't block, like a byte array output stream or something else, it will immediately return as you pass data into it. So those frameworks we could directly wrap. But the parsing side is more complicated. You might see some terms here you don't recognize, because in order to parse XML in a non-blocking way, the parser has to be able to say, hey, I read up here into the byte buffer that you sent to me, but I don't know yet what I'm going to do, because it might be an XML element that started here, or it might be some body. I actually have to see more data to make up my mind. And that's not a valid parser state in the standard Java XML parsers, because the only way they can parse data is by giving them an input stream. And they say input stream.read, and they expect to block the thread there until there's some data. And that's exactly what we didn't want to. So unfortunately, we can't use the built-in Java parser, Java XML parser. You can't use JSON either, because it's built on a similar model. Luckily, some other guys have taken the hard work of actually writing non-blocking XML and JSON parsers. So that's the Alto parser and the XOM parser for XML and JSON. So those we could wrap. The CSV part we took care of, which actually turned out not to be that complicated. The CSV is a little simpler. But these give us the basic building blocks to now have an ECA stream of XML events, or JSON events, or CSV events, and also to, if we have some XML events, to turn that back into bytes. So we could took part of the input and the output side of the equation. But now about the marshalling again, and now it starts to get interesting, because those protocol instances we talked about earlier that describe, okay, this is how I get my person or my other object to and from XML or JSON or CSV. The implementation of these interfaces is actually set up in such a way that it is fairly easy to turn that into an ECA stream. And that's what we provide for in the library when you have a particular protocol. So in this case, a protocol of a person, how to convert that to and from XML. You can actually you have a class called protocol reader that you can use to turn this protocol into a flow that goes from XML to person. There's another class called protocol writer that you can use to turn this protocol into a flow, an ECA flow of person to XML element, so to output again. So now, the other stuff that we have here, we can put all of that together to now create a processing flow where we start with some bytes on our input, again, reading from a file, reading from standard input. There are standard ways in ECA to write that. And we shove that through our parser. Now we have a stream of XML elements. Those we put through our unmarshal flow, which will now result in a stream of person elements. And remember that could be anywhere in the XML, depending how you write your protocol. You could say, okay, 6 levels deep in this set of sub-XML tags, I might see person instances, and there might be a great many of them. But because you're just linearly going through this XML, you don't start the unmarshalling until you're at the point of interest everywhere in the document that you're trying to reach. So now we're at person, and now sort of plain ECA can take over. You can use any of the built-in combinators. I don't want to go into that here, but you can convert that and do all sorts of strange and wonderful things with your person from here. In this case, I just create a simple flow that doesn't do again. Okay, so we just turn first name into uppercase. But then we can go to the reverse and say, well, I have my person, and I want to marshal that. So now we go from a stream of person to a stream of XML element again. And you have to take a bit more care, because now, of course, your protocol has to end up with valid XML. If you have a protocol that like we originally defined person, which just says tag person with this stuff underneath. If you have several persons that you emit into the same file, that's going to be a problem because XML can only have one root element. So you have to have a sort of a top-level tag that you define there so that you can iterate over something inside that top tag and then close it as the stream closes. But it's certainly possible to write, and you'll figure it out as you use the library. And after that, we just put the XML elements that we got from there through our XML generator, and we're back with byte string that we can then send out or do something else with. Does that make sense? Okay. Now, to give you a bit of an overview where we are with this, because of course we started with one use case, but we figured out that there are actually a lot of different related problems we can solve with this. So like any other thing, this started small and kept growing. Some other people contributed and got some ideas, and I got interested and wanted to use part of it. So yeah, but we're sort of covering a nice area right now. So what we have are a DSL for Java to say how you want to bind XML and JSON and CSV, and that's fully there. For XML, like namespaces and everything you would expect is there to cover your XML processing needs. Remember, we're using it for UBL, which is a wildly complex specification, and it deals with that just fine. Besides that, we have bindings for Java collections and for a library called Java Slang. Who of you have never heard of Java Slang? Okay, I definitely recommend you check it out. It's a library that provides an alternative collection framework that focuses on immutable collections. So if you do anything related to concurrent programming, like these streams, like doing stuff in parallel, you quickly find out that if you have a mutable class, you're fucked, because you have this class you share, but not a thread. They both try to change it and things blow up. And then you say, okay, I need to make my objects immutable. But as you see, as soon as you use a list or array list in Java or something else, you have to try really hard to maintain that immutability. And just by using something like Java Slang, the default is immutability. So you sort of roll with that, and there are just less mistakes to make. And Scala bindings we're also working on. There's some other nicer, cooler things that you can do once you're at the level of having a stream of XML elements. So like I said, okay, you want to start marshalling when you hit a particular part of the XML document. Like in our case, you want to see only the attachments. We actually have a class called protocol filter, where you can put a protocol in and some sort of subgraph that you want to be invoked when that particular protocol matches, and you can use that as a flow stage in your XML processing. And what you can do with that is say, okay, when this particular piece of XML is read, and of course the read protocol, you can think of that like an XPath expression or something else, where you say, okay, I want to match this part of XML. But now you can actually say, I want to send this part of XML through a different part of our processing graph than the rest of the document. And in that way, you can sort of split off parts, do a selective transformation, ignore them completely to remove them, or do anything else, and the result still is one processing graph, so you retain all your nice non-blocking processing concepts. A second thing which we put in is, it seems to be a fairly simple thing, a way to validate an XSD schema. And actually the wrapping itself is fairly simple, because luckily the Java's way to deal with XML schemas does allow you to just send XML events into the validator object, and in the end it will say if something is valid or not. But that actually triggers a nice anecdote. Remember, we were dealing with these 100 megabyte documents, right? And we were sort of halfway along in having implemented this library and doing some testing where we say, okay, we want to throw out all the attachments and deal only with the body content. And with a performance test where we say, okay, we want to lower the heap size quite considerably to prove that we don't have to keep all these things in memory. But no matter what we tried, memory usage didn't go down. It was still in the hundreds of megabytes like per document that we were processing. We were pretty sure it wasn't our stream because it was fairly linear. As it turns out, the XML schema implementation that's in the JDK, I'm pretty sure they didn't bother to fix that since I checked. If you say in your schema, hey, the content of this element must be base 64, it's sort of a top-level XML type, base 64. Because base 64 basically means you need to have 0 to 9 and a B. No. You need to have the ASCII set there, plus a few extra characters, and that sort of encodes binary data. But there are no other rules. It's just those characters must occur in the content, and then it can end with a few equal signs. Those are basically the rules. So how would you implement a validator for that? Well, the people that wrote the XSD implementation in Java thought, well, let's read in all the content that we have and keep appending that to using a string builder until the end of the base64 stream is found, and then let's run through it and see if it's valid. There are two big problems with that. The first one you see, obviously it uses a lot of memory, but it actually uses twice the amount of memory that it needs, because string builder internally, when it reaches the end of its capacity, will double its capacity every time. So you're at 64K, 128K, 256K, and then if you're at 1 meg, 2 megabytes, imagine the crying involved. So we actually now only validate the non-base 64 parts. So it's the only way to do that. Let's look at some actual code. Maybe for funsies, I will try and bring up my IDE for that. If I can, yeah, that ought to work. So on the XML side, to have something that may be a little easier to comprehend than a full-blown UBL invoice, I figured, well, we probably have seen in some of the XML frameworks or some other stuff that we've seen, like a properties file where you have a property name is this, value is that. Unfortunately, some frameworks use that for when you need to shoehorn stuff into properties, but others, like Maven, has where the property name is the tag, and then you have the value in there. And I figure, right, let's see if we can write a stream that converts one to the other, because it would be a nice showcase of what we have. And that's what you see below here. So let's start with the read protocol, where we want to say, well, the root tag of our document, because remember these properties, they don't live on their own in the file. There's always a root tag called properties or settings or config or whatever it is. But here, when we're reading it, we don't care what the root tag is. We're interested in the stuff that happens one level below that. So we say any tag, which just has the one argument, which is the nested protocol that we want to happen in there. And we're going to read a tag called property. And we're interested in two things inside that tag: attribute name and attribute value. Now, because of this particular variant of tag, since you have two elements, it'll actually return a class from Java slang called tuple2. In case you don't know that, it's just a generic type that combines two strings without bothering to give the names, which you really shouldn't ever do except when presenting. And here we have our tuple2 of string and string, which will contain the key and the value of that particular XML element when it was read. Now we can create an out proto as well, which is the way we want to represent them going out. And there's a helper thing again in our list of XML protocol definitions called any tag with body, and that's a protocol for a tuple of a qualified name and a string, where the qualified name is the name of the tag, and the string is the body. You can just follow that if you were to control-click it in your IDE. This is a static field, the documentation and some other stuff, or you can see that what rolls out there is QNAME string protocol, which is still a protocol that takes XML elements and has a the signature isn't that obvious, but this is a T-string protocol that reads XML elements. QNAME comes from Java itself, but T-string is then a protocol that actually has a tuple in it. That was made generic so that you could do some additional operations on the string involved. But what rolls out of this would be a tuple of QNAME and string, but we're not interested in the qualified name. So the qualified name in Java is something that has the XML namespace and the XML element name. We just care about the name. So we say that as local name, which then gives us just the tuple of two strings. Now, in a similar way that we've seen before, we can now create the source one step at a time and say, well, let's start by reading from our system input. We now get a source of byte strings, put it through the auto reader to get a source of XML events, run it through the protocol reader of our input protocol. So now we have a string of tuples of string and string. And we output them directly again through the out proto, which gives us back a stream of XML events again. We run that into stacks to actually output bytes, and that goes to our standard output. And then there's, in the end, we say, well, let's actually run this stream. And by the way, when we're done with it, I want to shut down the underlying framework as well, because if this is a command line application, you don't want it to stick around when it's done, you just want it to exit. Of course, there's a lot of code and a lot of types in here that you might think, okay, can we clean this up a little bit? Which you can do, since all of this is just an expression that you can pull together, and then depending on your preference, you will land anywhere between these two representations. But you can actually fold all of this in and just say, well, we start from system in through alto and run through a protocol that's made up of these tags over here, and turn it out into another protocol that looks like this, instead then materialize it again. And again, as your level of comfort increases or decreases, you can write in any of these ways. I want to go back a little bit to the start use case before we finish up. So remember our big XML invoice document. In the system that we're writing, which is going to replace our current document processing eventually, what we want to do is, as this potentially huge, of course we also have small documents, but as this potentially huge document comes in, we want to, on the fly, extract all these attachments and put them into S3, one each. So each attachment tag, we want to base64 decode and find the actual file and put that into S3 to store that. And by the way, replace the actual attachment tag with a different tag that's an attachment reference, where we put the key that we picked to put it into S3 and put that in there, so that the invoice that we actually store still semantically is equivalent to what we got, but there's still a way to get back to the attachments. We don't want to just delete them. We want to remember that there was an attachment, and also, if someone's interested, still be able to read it back. We don't want to just throw away the data. And then the resulting invoice should go into S3 as well. And remember, we want to do this without buffering it, and disk in memory anywhere, and without blocking a thread ever. And we were able to do that. The resulting graph looks a little bit like this, summarized, where you start with your string coming in, we parse it into XML, and then every time we see an attachment, we start a new subgraph. So that you can do. You can sort of selectively split something into separate processing steps in Akka, which then results in 3 different processing pipelines, one for the first attachment, one for the XML events to make up the second attachment, and then if there are no more attachments, there's just the rest of the body beneath that, or actually the part in front of the attachments as well. And if something is not an attachment, it will just go through unchanged. But if something is an attachment, and for each of them this applies, we put it into a base64 decoding stage, and then put it into an S3 upload stage. But again, that's not just a method that says, please take this document and upload it to S3, because the upload to S3 has to be itself a stream. So the actual HTTP connection to S3 is actually part of the graph, to the extent that if, for example, it's a bad example, but if S3 becomes slow, it would actually back up the graph all the way back to the input, and the reading from the actual REST request that is stored in the document would also slow down, just because the graph in the end is blocking. A little bit like your input stream example would be, just without having to block a thread. But all the subgraphs, when they're done, the attachment, we also replace that with the reference. We concatenate all these things back together, hopefully in order, turn it back into bytes and shove that into S3 as well. And as it turns out, the scaling part of this does work, because I've been hammering down on the not blocking a thread while having huge documents, and that in itself doesn't make much sense, because if you have a huge document anyways, the number of concurrent documents you can handle on your server is limited, so why bother with the blocking a thread on it? But we also want to use this for the vast majority of invoices, which are actually pretty small. And there we do want to be able to handle 1,000 or so, depending on your server size, but quite a few concurrent requests, because in the end, all you're doing here is shoving data in and out. So your server doesn't need to do much, so it should be able to handle quite a few concurrent connections. And there you cannot afford to block threads. So we needed to implement the big use case while still being able to also handle the small use case. And that we are able to do. So what we've seen is that without any magic, we can actually create a way to represent the marshalling of Java objects in Java without introducing a lot of concepts. Of course, there's the protocol thing that you have to learn and get used to, but you can click and find any part of the code that is used and find out what does this do, how does this affect the XML stream or the JSON stream. So in that sense, you have to rely a lot less on specifications and documentation to work with this. Composability is also a lot nicer because in the end, the protocol is a Java object, so you can reuse that. You can create a function that returns the protocol and customizes it depending on what you want. And I actually haven't talked about testability, but let me ask you a quick question. You said that you've all used JXB before. Who of you has written unit tests for your JXB annotations? So how do you know they work? Have you written component tests for the thing itself, for your REST API then? So you write these annotations and you sort of believe in God that if you say XML element this, that it actually does that. But why does it do that? Yeah, we all know frameworks don't have any bugs, and I'm sure with XML element, yeah, it's probably going to do it. But as you get into the more complicated use case, like we look in, you have to have a type annotation here that gets called into there, and then have an injector, and it becomes very hard to test. Whereas, again, if your XML mappings is just code, you can just write a unit test. You say, turn this into XML, see what comes out, and that to us is very valuable because it means that when you write an API, you can guarantee that it looks the same over releases, or if it breaks, or if it changes, you can be explicit about that. So, if you want to try this out, there's a GitHub link to our TS Reactive library that sort of builds on Akka to make this possible, that you can try right now. There's also an ongoing pull request to get it into a side project of Akka itself. And if you want to reach me or other people that are doing this kind of stuff directly on chat, there's a Jitter channel on Akka that you can reach me in usually. Any questions? Otherwise. Yes, this is definitely new. So if you need if you don't have this particular use case, this may not be what you're looking for. But I would argue that, especially on the annotation-related thing on JXB and Spring, there are enough death traps there as well that it may be old technology, but it doesn't make it proven. It's just it has more exposure because it's in the spec. And I think what I'd like you to take away from this talk is that there are more down-to-earth approaches to something that we take for granted, like XML marshalling, that can actually give you a lot more confidence than JXB would give you. So yeah, we are definitely using this. There are more and more projects that we use internally. But as you can see, it's just now getting accepted by a broader community. But yeah, we'll see where this leads. As you see from the previous talk, there's definitely a movement away from magic into more explicit things, and especially with Java 8 having gotten lambdas, a lot of the things that we would earlier reach for annotations in, these days you really would do something with lambdas instead. And I wanted to present this to show that marshalling, I think, really is one of those as well. It's not necessarily going to be this framework, but I think that something that is closer to our source code is always a good idea. Thank you.